Hello there and welcome back to the Sleep Science. Tonight, you're floating. Not metaphorically, you're drifting weightlessly through space. The kind of space that's not just empty, it's frozen. There's no wind, no up or down, only the gentle pressure of your own breath in a suit that's the only thing between you and a cold so deep it doesn't just bite, it swallows. Tiny specks of starlight blink from impossible distances, and somewhere far behind you, Earth spins on in its toasty little orbit. But here you're in the nowhere in particular part of the universe, where the sun is a faint memory and the darkness doesn't just surround you, it becomes you. The silence hums in your ears, not because there's sound, there isn't, but because your brain doesn't quite know what to do with the absence. This is not the cinematic cold of a glacier or the winter wind screaming through pine trees. This is deep space chill. The kind of cold that doesn't even know you exist. It's not trying to kill you. It doesn't care enough to try. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're really cozy tonight, drop your location and local time in the comments below. Let's see who's falling asleep under which patch of stars. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're drifting now, toward a place where the universe stops pretending to be friendly. The nearest planetary warmth is light hours away. You've entered the cosmic deep freeze, regions of space where temperatures plummet to just above absolute zero, the coldest temperature physically possible. But you probably won't survive this. Even the toughest spacecraft insulation would struggle out here. If your visor cracked, your breath would crystallize before it left your mouth. Your eyes would boil and freeze at the same time. Isn't that comforting? This is the kind of environment where molecules stop moving. Not slow down, stop. Where atoms barely vibrate, suspended in a timeless vacuum. It's quiet, yes, but not dead. Radiation still pulses here. Subatomic particles still flicker into being and vanish. And far off, maybe a rogue planet tumbles silently, carrying heat in its core like a fading ember. Historians, well, physicists really, still argue whether the vacuum of space is truly a perfect vacuum. Some say there's always something, a particle here, a whisper of heat there. But even those minimal things don't warm the place up much. The background temperature of space, thanks to ancient leftover radiation, hovers around 2.7 Kelvin. That's minus 270.45 degrees Celsius. So if your socks feel cold tonight, remember, they could be much colder. Still, the coldest areas of space aren't evenly spread out. Some pockets are colder than others, and where you are now, let's say near an interstellar void, there's less of everything. Fewer stars, fewer galaxies, fewer chances for a stray warmth-bearing photon to stumble into your little corner. Even the light here has given up. You pass a lonely bit of space debris, maybe a chunk of rock from some ancient collision, or a piece of a probe long dead. It's been orbiting nothing, baking on one side and freezing on the other. Temperatures here are tricky. In direct sunlight you'd roast, in shadow you'd shatter. Space doesn't do room temperature. Still, this isn't the coldest space can get, not by a long shot. There are places where the thermometer dips even lower, and we'll get to those. But first, you settle into this sense of weightless drift, the kind of float that only happens when gravity lets go. You feel it in your shoulders, in your jaw, in the way your thoughts start to slow. The quiet of this frozen cosmos is the kind that seeps in, cools your pulse, hushes your nervous system. It's hard to imagine life out here, and for the most part, you're right not to bother. But extremophils, those tiny, unreasonably hardy organisms, exist in Earth's coldest places, and some scientists believe similar creatures might survive beneath the icy crusts of moons like Europa or Enceladus. The notion of something living, breathing, multiplying in environments that mimic the cold of deep space? It's not entirely fantasy. And yet, even the most optimistic astrobiologist would admit, this place? Probably not. A fringe theory even posits that the universe's coldest pockets are necessary for consciousness to form, something about entropy and low-energy information fields. The theory hasn't caught on outside a few academic corners, but it does make you wonder. If cold brings silence, and silence brings thought, maybe this is the thinking part of the universe. Or maybe it's just empty. You spot a satellite now, dead and tumbling. Once it was a tool, a marvel of engineering. Now it's a frozen relic, a popsicle of progress. Somewhere, it still holds code written in languages half forgotten. And if it collided with something out here? No bang. Just a quiet shattering and a puff of metal shards that would never melt. Back on Earth, we simulate this kind of cold in vacuum chambers, cryostats, and space simulators. But no chamber can replicate the sheer loneliness of it. The absolute distance. It's one thing to hit minus 270 degrees Celsius in a lab. It's another to be minus 270 degrees Celsius away from anything that remembers warmth. One historical note for tonight. When Sputnik launched in 1957, it became the first human-made object to experience the temperature swings of space, plunging into cold shadow, baking in sunlight, and back again with each orbit. Engineers learned fast that space wasn't simply cold, it was worse, it was unpredictable. So now, as you spin slowly past a patch of gas barely warmer than the void itself, you realise how strange it is that the universe, once unimaginably hot, now mostly chills in this freezer box state. It makes you wonder where the heat went. Spoiler, we'll get there. But for now, you drift, breath shallow, muscles soft. You don't need to understand cosmic background radiation or entropy gradients. You just need to feel the coldness of it. Let your thoughts slow like molecules in a vacuum. There's nothing chasing you here, nothing to run from, just silence and frost and the quiet truth that in the grand ballet of the cosmos, even fire has its ending. There's a number that gets whispered in physics halls like a ghost story, 0 Kelvin. Not 0 Celsius, not 0 Fahrenheit, 0 Kelvin. Also known as absolute zero, it's the bottom floor of the thermal universe. A place, theoretically, where all motion stops, not just your fingers going numb or your coffee cooling too fast, but where the atoms themselves cease to jitter, vibrate, or whisper. It's the coldest temperature that can exist, a frigid silence embedded into the laws of nature. But here's the twist. You can't actually get there. Not really. Right now, as you continue to drift in this deep freeze cosmos, you're surrounded by temperatures that edge achingly close to that number. Negative 273.15 degrees Celsius. That's just 0.00001 Kelvin. So close. But just like trying to reach the edge of a rainbow, or actually touch a mirage, nature has locked absolute zero behind a door no one can open. The closer you get, the harder it becomes to close the final gap. Physics has written it in. You can approach it forever, but you'll never arrive. That's comforting in a weird way. Even in the coldest dark, something always moves. Some wobbly little quark doing a shimmy, a ghost of heat refusing to die. You might be frozen solid out here, but the universe won't quite stop moving with you. Scientists have built entire experiments around this boundary. Lasers, ironically, are often used to cool atoms. By firing them at just the right frequency, researchers can cancel out atomic movement, like a cosmic noise-cancelling headphone for matter. It's how we get Bose-Einstein condensates, those weird states of matter that start behaving more like waves than particles. At near 0 Kelvin, atoms stop acting like atoms and more like thoughts, dreams, mush. Back in 1995, when physicists first created a Bose-Einstein condensate in a lab in Colorado, the temperature was just a few billionths of a degree above absolute zero. That's colder than the vacuum of space. It made headlines, but even then they didn't hit the magical zero. Nobody has, not even in a lab, not for a trillionth of a second. Meanwhile, in the natural world, out here in the emptiness between stars, temperatures hover just above that impossible 0 point. The coldest natural object known so far? It's a nebula we'll visit later, one that somehow dips to about 1 Kelvin, which makes your freezer seem like a hot tub. But even that chilly mist hasn't quite hit the bottom. Historians still argue whether the idea of absolute zero originated with 17th century experiments or 19th century thermodynamics. The concept definitely matured during the Industrial Revolution, when engineers and physicists started asking questions like, how cold is too cold? And can we use temperature to do work? It wasn't just academic, it was practical. Steam engines, refrigeration, even the light bulb depended on understanding heat and its limits. But here's the quirky fringe bit. There's a school of thought, mostly philosophical physicists and some speculative thinkers, that wonders if there might be temperatures below absolute zero, negative Kelvin. It sounds like something your moody cousin would claim when they're colder than cold, but it's actually a real thing. Under extremely controlled conditions, like with lasers and magnetic fields, scientists have created systems that behave as if they're below 0 Kelvin. The particles in these systems don't calm down. They get more energetic as you cool them. Wild, right? You're not floating in a negative Kelvin pocket right now. That would be wildly unstable, and not something you'd want near your vacation home. But knowing such places can exist, even temporarily, makes you wonder just how much wiggle room the universe has around its supposedly unbreakable rules. And speaking of rules, the third law of thermodynamics is the main gatekeeper here. It says you can't reach absolute zero through any finite number of physical processes. It's like trying to roll a ball up a hill that gets infinitely steeper the closer you get to the top. You can try, you can come so close. But the hill always stretches a little farther. Out here, drifting past a lonely cloud of gas and dust, you think about your own warmth. The blood in your veins, the slight heat from your thoughts, even the gentle puff of air from your breath. All of it is heat. You're a tiny furnace in a place that forgot fire 1 billion years ago. Every biological process inside you depends on not being this cold. Even the coldest creatures on Earth, the Arctic springtails, the wood frogs that can freeze half their bodies in winter, are nowhere near this level of cold. They survive by slowing down, going dormant, but always with a flicker of metabolic ember. The cosmos doesn't do embers. It either burns with furious fusion or fades into glacial darkness. There's a poetic fairness to that. After all, if heat is energy, and energy is life, then cold is the universe's waiting room. Not death, exactly, but the pause between events. It's where things go to be forgotten. Meteorites wander here for millions of years. Forgotten comets skate by, frozen silent. Occasionally, a flash of heat from a passing star warms a bit of dust, and for a second, just a second, there's motion again. Then it's back to 0-point dreams. As you drift, maybe you wonder what your own atoms would do, chilled this, close to nothing. Would you dream slower? Would your thoughts crystallize? Would you forget everything or remember it all perfectly? Strange how the cold doesn't dull the imagination. It sharpens it, carves it into thin, glassy layers. You start to see the patterns beneath the frost. Even now, someone on Earth is building a better cold trap, trying to shave one more decimal off that temperature, just to see what's possible, just to see what stops. So you keep drifting, caught between what can be measured and what cannot. The space around you doesn't change much. There are no clouds rolling in, no sunrise, no ticking clock. Just cold, not quite absolute, but close enough to hear it whisper. Somewhere deep in your drifting, the universe begins to rewind. Not in time exactly, but in temperature. It's hard to imagine, but this frozen cosmos was once unimaginably hot. The kind of heat that could vaporize atoms before they had the chance to form. No stars, no planets, not even the idea of cold existed yet. Just pressure, energy, and expansion. And then, boom. Or rather, not quite a boom. The Big Bang wasn't an explosion in space. It was an expansion of space. Everything, everywhere, all at once, stretching outward from a single point of infinite density. The moment it happened, heat reigned supreme. We're talking trillions of degrees Kelvin. Entire universes could boil in a blink. The early cosmos was a searing, luminous soup of particles too energetic to settle down. But nothing stays hot forever, not even the whole universe. As space expanded, the energy spread thinner, like a drop of dye diffusing in water. And with that spread came a slow, inevitable cooling. The baby universe aged fast. In the first microseconds, it went from white-hot plasma to merely star-melting temperatures. Eventually, it became cool enough for electrons to hook up with protons and form the first atoms. Mostly hydrogen, a little helium. Simple things, floating through a darkening cosmos. This cooling process didn't just make atoms possible. It made everything possible. Galaxies, stars, you, lying in bed, listening to space stories. If the universe had stayed hot, it would have been a light show with no audience. But instead, it started to chill. Historians of science still argue whether the term Big Bang helped or hurt public understanding. It was actually coined as a joke by Fred Hoyle, who favoured a steady-state theory instead. But the name stuck, and now it's the single most popular explosion that never actually exploded. Fast forward to about 380,000 years after the beginning, not much in cosmic terms, and you get a moment known as recombination. No, it's not a rock band or a salad bar. It's the era when the universe finally cooled enough for light to travel freely. Before this, the cosmos was opaque, like a fogged-up mirror. But at 3000 Kelvin, still hotter than lava, electrons and nuclei stopped fighting and settled into atoms. Photons finally broke free, zipping through space. That ancient light is still out there, frozen in time. You'll meet it again soon. But even after recombination, the universe had a long way to go before it felt anything like cold. The early stars lit up around a few 100 million years later. Great blazing furnaces, forging heavier elements in their cores and blasting radiation in every direction. These were not your friendly neighbourhood suns. They were giants, short-lived, furious and spectacular. Their death seeded the cosmos with the ingredients for planets and people, but they also kept things relatively warm, at least in their local galactic neighbourhoods. Still, in between the stars, cold reigned. A darkness stretched between galaxies filled with dust, stray hydrogen and silence. The larger the universe grew, the colder it became. It's like baking a cake and then leaving it on the windowsill. Except the cake is everything, and the windowsill is infinity. You drift now through one of these dark spaces, where the only visible structure is a wispy cloud of interstellar dust. It barely glows. If you could touch it, which you can't, it might be just a few degrees above absolute zero. Still enough heat to count, but not enough to feel. A quirky historical footnote here. In the 1940s, a physicist named George Gamow proposed that if the universe began hot, it should have left behind some residual glow, afterglow from the Big Bang itself. He and his colleagues even predicted its temperature. But it wasn't until 1965 that two radio engineers, Arno Penzias and Robert Wilson, accidentally discovered this cosmic background radiation. They were trying to get rid of an annoying hiss in their antenna. Turned out the hiss was the universe, still echoing from its own birth. Oops, the background radiation has cooled a lot since then. It started off around 3000 Kelvin and is now just 2.7 Kelvin, roughly negative 270.45 degrees Celsius. That's what happens when you let 13.8 billion years go by. Everything cools off, including you, if you stay out here long enough. The universe's current state is a direct result of that first fire fading. It's a cosmic paradox. The universe started in a moment of maximum heat and density, and it's ending, maybe, in a state of maximum cold and emptiness. From chaos to calm, from fire to frost. You wonder, drifting in the dark, whether the cold you feel now is the echo of that first heat, or simply the absence of new heat being made. There's a philosophical angle to it. Cold not as a thing, but as a silence. A stillness left behind when everything loud has burned out. A few speculative physicists have played with the idea that time itself might flow differently in the cold, that perhaps the passage of time is linked to entropy and thermal activity. In absolute stillness, would time freeze too? It's more thought experiment than solid theory, but it does make you wonder what kind of clocks the universe keeps out here. You pass what might be a protogalactic cloud, just a loosely bound chunk of hydrogen atoms, not yet condensed into stars or planets. It's billions of years old and still waiting to become something. Or maybe it missed its chance. Maybe it'll drift forever, quietly cooling, a failed audition for a galaxy. The cold in this part of space isn't just a backdrop, it's a sculptor, shaping what can form and what cannot. Gas won't collapse into stars unless it cools down. Planets won't hold onto atmospheres unless they avoid boiling. Cold is not passive, it's selective. It decides what survives and what simply drifts. Eventually your trajectory will bring you close to one of the oldest, coldest witnesses of this process, the cosmic microwave background, that pale ancient light that fills every inch of the sky. But not yet. For now you remain in this quietly receding place, where the first great heat still echoes faintly, cooling, stretching, dimming into silence. The Big Bang lit the match, but what you feel now, the hush, the stillness, the bone-deep chill, is everything that came after. You don't see it at first. It isn't a flash or a flare. It doesn't wave hello or shimmer with mystery. It's everywhere and nowhere, like a whisper that's been echoing for so long you forgot it was there. But you feel it. A gentle hum, not of sound but of warmth, long faded. It's the cosmic microwave background, or CMB, and you're bathing in it right now whether you realise it or not. It's the oldest light in the universe, and it's still glowing. At just 2.7 Kelvin, it's barely above absolute zero. Not enough to boil water, toast bread, or even melt ice. But it's there, a soft bath of microwave radiation that fills every direction of space. You could turn your head any way, float to the edge of any galaxy, and it would still be with you. A thermal hug from 13.8 billion years ago. The universe's original group photo, pixelated and stretched beyond all recognition. This light, if you could see it, wouldn't twinkle or dazzle. It would be dull, uniform, quiet, like a grey fog overlaying all of space. But that fog holds secrets, tiny fluctuations, microscopic hot and cold spots, different by mere millionths of a degree. And from those wrinkles, galaxies grew, stars were born. Those gentle ripples are the fingerprints of everything. It's strange to think that your microwave at home picks up traces of this signal. About 1% of the static on an old-school TV, that's the CMB. So next time you're fussing with your remote or cursing your popcorn for burning in the middle, remember, you're arguing with a relic from the dawn of time. This light was released during the recombination era, that sweet spot when the universe cooled enough to let photons roam free without bumping into everything. Before that, the cosmos was a plasma stew, particles ricocheting like bumper cars. But once the temperature dropped to about 3000 Kelvin, the fog lifted and the light escaped. That's what you're feeling now, stretched thin by 13 billion years of expansion. What once shone in visible light now glows in microwaves, like a leftover pizza that's been reheated far too many times. The CMB isn't just a backdrop, it's a map. In 1992, the COBE satellite confirmed its uniformity. Then, in 2003, the WMAP mission revealed the little bumps and dips that helped build the universe. And later, the Planck spacecraft refined it further. We've painted the most accurate portrait of the infant universe using a signal that's colder than dry ice. Historians still debate who should get the most credit for predicting the CMB. George Gamow, Ralph Alpha, Robert Herman, they all had a hand in it. But as usual, scientific credit is a slippery fish. What's not debated is the impact. The discovery of the CMB is one of the strongest pieces of evidence we have that the Big Bang wasn't just a theory, it was an event. A ridiculously, incomprehensibly, universe-defining event. And here's your quirky tidbit for tonight. In the 1970s, a group of Soviet scientists proposed that the CMB might not be from the Big Bang at all, but instead, the glow of light reflecting off iron particles drifting through the cosmos. It wasn't true, but the idea was poetic in its own way. A universe coated in cosmic glitter, still glowing. But the truth is even better. The CMB wraps around you like a memory, a sort of cosmic lullaby humming from every square inch of the sky. It doesn't change, it doesn't blink, it just is. You pass now through a part of space where the CMB's presence becomes oddly comforting. There are no stars here, no planets, just dust and darkness and this gentle thermal ghost. It's the faintest kind of warmth, the kind that doesn't raise your temperature but lets you know you're not alone. In fact, it's proof you never have been. The entire universe shares this light with you. Every star, every black hole, every particle, it's all marinating in the same soft glow. And yet, the CMB is fading, slowly but surely. As the universe continues to expand, this background radiation gets stretched thinner and colder. In another few trillion years, it may drop so low that it becomes undetectable. Future civilizations, if any survive, might look out into the cosmos and see no trace of the Big Bang at all. Just stars, galaxies, and silence. The echo we take for granted today will one day be gone. In a sense, you're lucky. You're floating in a time when the universe still remembers its own birth. You can listen to its heartbeat, however faint. One day, even that heartbeat will fade, and the stars will whisper alone. Of course, the CMB doesn't offer much comfort physically. It won't warm your face or power your ship. It's less a fireplace and more a memory of one. But it gives you orientation, a sense of place. You're not just drifting through random cold, you're drifting through history, through a light that predates everything you've ever known. Some physicists describe the CMB as the universe's baby picture. Others say it's like the afterglow of a cosmic fireworks show. But maybe it's more like the warmth of a campfire long after it's gone out, the heat no longer present but the scent of smoke still in the air. You drift on now, past voids that echo with silence, toward colder places still. But in every direction the background glow remains. You can't hide from it, and you wouldn't want to. It's the most democratic light in existence. It doesn't care where you are or what you've done, it simply is. And as you float, you realise this light doesn't demand anything from you. It just wraps you gently, a whisper of ancient fire stretched across time and space. You're not just floating in the cosmos tonight, you're floating in its memory. You turn now, slowly, your trajectory nudging you toward a spark in the distance, not bright, not blazing, but faint, like an ember buried in ash, a star. But not the kind you imagine when you picture constellations twinkling over a warm night on Earth. This one is old, small and cool, by stellar standards anyway. A red dwarf, quietly sipping hydrogen and refusing to die. The universe is full of these chill little stars. In fact, they outnumber their hotter cousins by a ridiculous margin. Roughly 75% of all stars in the Milky Way are red dwarfs, and yet you've probably never seen one with your naked eye. That's because they're not particularly flashy. They don't explode. They don't glow like celestial bonfires. They just hang there, dim and persistent, like the pilot light on an old gas stove. This one you're drifting past now is cooler than any star you've ever considered. Surface temperatures can be as low as 2,500 degrees Celsius, still hot enough to roast a marshmallow at record speed, but in stellar terms, that's practically chilly. Compare that to the Sun's 5,500 degrees Celsius, or the insane 40,000 degrees Celsius of a blue giant, and it's clear. This little red thing is the universe's version of a cardigan and a cup of tea. Despite their low energy, red dwarfs are overachievers when it comes to longevity. A typical one can burn for trillions of years. Yes, with a T. That's longer than the universe has existed so far. Our own sun is middle-aged and will eventually sputter out in another 5 billion years or so. But red dwarfs, they're in it for the long haul. They burn their fuel with extreme frugality, like a miser hoarding candles in a blackout. Historians still argue whether our focus on sun-like stars in the search for habitable exoplanets has caused us to overlook red dwarfs. Many of these little stars have rocky planets in their orbit, and some are even in that coveted Goldilocks zone, where liquid water could, in theory, exist. But red dwarfs are tricky. They can be moody with flares that spike in radiation. The light they emit is reddish and faint. You wouldn't get a blue sky on one of their planets, more like an endless rust-coloured dusk. And yet, life might thrive there, slowly, quietly, maybe even under the surface, shielded from flares and basking in geothermal heat. Some astrobiologists believe that red dwarfs could be the best hope for long-term life in the universe, assuming anyone's got patience for a 10 trillion year lease. A quirky, lesser-known fact. In 1994, astronomers discovered a class of objects called ultra-cool dwarfs, even fainter and colder than typical red dwarfs. They blur the line between star and planet. Some are just massive enough to fuse deuterium but not hydrogen, which makes them technically brown dwarfs, the awkward teenagers of the stellar world. They don't shine so much as they smoulder. And if red dwarfs are cardigan stars, brown dwarfs are the ones wearing 4 layers, huddled near the cosmic radiator, hoping nobody notices them. You might drift by one and not even know it. It could be darker than the void around it. Only infrared telescopes reveal their soft thermal glow. You ease past your current red dwarf, watching as its weak light stretches across the nothing. It doesn't cast shadows, it doesn't warm your skin, but it hums with age. Maybe it's been burning since shortly after the Big Bang, and it'll still be glowing when all the other stars have turned to dust. There's a kind of stubborn dignity to that. Here in the frozen cosmos, these cool stars act as tiny hearths scattered across a vast icy plain. They don't invite drama, they offer consistency. No supernovas, no black hole theatrics, just the quiet process of fusion, chugging along at a gentle pace, and yet, from Earth, we barely register them. Our astronomy books focus on the bright guys, the Betelgeuses and the Rigels, the dazzling ones that flare up and die young. It's kind of like real life, isn't it? The loudest people get all the attention, but it's the quiet ones who endure. You spot another ember, this one even cooler, possibly a late-stage red dwarf on its way to becoming something even stranger. A white dwarf, perhaps. When a red dwarf finally uses up all its fuel, which takes longer than the universe has existed, it doesn't go out with a bang. It doesn't collapse into a black hole, it just shrinks. It condenses into a hot, dense core about the size of Earth, no longer burning, just glowing from residual heat. A cosmic memory, pulsing faintly. But that's for another leg of your journey. For now, you stay close to the red dwarfs. They may not keep you warm, but they keep you grounded. Their predictability is a comfort, like a space heater that's been on for trillions of years and still hasn't blown a fuse. In the far future, when the universe is cold and dark and most of the galaxies are fading from view, these little stars might be all that's left, lighting the long night with their quiet resilience. A few trillions of years. Later, even they will blink out. But until then, they'll carry the warmth of creation forward, one tiny flicker at a time. So as you drift past this slow-burning flame, remember, not all stars are born to dazzle. Some are born to endure, and in a universe where cold wins in the end, that endurance might be the greatest light of all. You float onward, leaving behind the gentle flicker of the red dwarf, and ahead, a darker kind of light begins to glow, a sharp, blue-white pulse from something far smaller and far stranger. It doesn't radiate heat so much as history. This is a white dwarf, the collapsed core of a once spectacular star, a stellar ghost, a husk, the remains of something that once burned 10,000 times hotter than anything you'll ever touch. Now it's just cooling. When a medium-sized star, like our Sun, reaches the end of its fusion fuel, it swells into a red giant, throws off its outer layers in a planetary nebula, and leaves behind a core that contracts under its own weight. That core, no longer burning hydrogen, becomes a white dwarf. No fusion, no fire, just heat leaking out into the cold. Think of it like a coal after the fire's gone out, still hot but not creating any more flames. These stellar remnants are dense, not dense like a rock, dense like a teaspoon of this stuff would weigh several tons. The atoms inside have been squeezed so tightly that electrons don't orbit nuclei anymore. They exist in a quantum pressure cooker called electron degeneracy. It's exactly as cozy as it sounds. And even with all that heat and pressure, a white dwarf cools. Slowly, painfully. Over billions of years it radiates its stored heat into the abyss. No fresh fuel, no second act. It just gets dimmer, colder, fainter. Eventually it may become what physicists call a black dwarf, a hypothetical object so cold, so dark and so ancient that it radiates no light at all. Historians still debate whether the universe has had enough time for a black dwarf to even exist. Most estimates say it'll take a quadrillion years, give or take, for a white dwarf to cool that much. Considering the universe is only about 13.8 billion years old, we haven't seen one yet. But in theory, they're waiting in the wings. Future archaeologists of the cosmos might dig them up like galactic fossils, stars that stopped shining long before anything noticed. The white dwarf you're drifting past now is doing exactly what it's supposed to do. Nothing. It just sits there, glowing faintly. It might still be hot, upwards of 100,000 degrees Kelvin on its surface, but without fusion, that temperature is only going one direction, down. Like the last breath of a long-forgotten fire still whispering into the dark. And here's a quirky tidbit. In 2020, scientists detected a white dwarf that had crystallized. Yes, crystallized, like a giant diamond the size of Earth, floating in space. The core of these stellar corpses can freeze into a crystalline lattice of carbon and oxygen under immense pressure. So next time you see someone flashing a ring, remember that there's a cosmic version 1,000 trillion times bigger, drifting somewhere in the constellation Centaurus. Some white dwarfs still have a little flare left in them though. If they're part of a binary system, they might steal material from a neighbouring star. Greedy, tired and a bit unstable. Same energy as someone finishing their roommate's leftovers at 2 a.m. If they accumulate enough mass, they can reignite briefly and explode in a violent Type Ia supernova. But most just dim quietly. No dramatics, just a gradual surrender to entropy. You hover now near the surface of one, not too close. Gravity is still unforgiving, and a fall would be swift. The light it gives off feels more clinical than comforting. It doesn't flicker or pulse. It just radiates in that constant, impersonal way that heat does when it has nowhere to go, like a radiator in an abandoned building still ticking. From this vantage point you can see the subtle colour shift, a pale blue-white but beginning to fade into the faintness of space. Its once intense ultraviolet radiation has calmed. Its magnetic field, still powerful, pulls at the thin clouds of nearby interstellar gas, but no planets orbit this corpse. No life clings to its memory. It is utterly, profoundly alone. You start to wonder, what would Earth be like when the Sun reaches this phase? Billions of years from now, after the oceans have boiled and the atmosphere has drifted away, after the red giant phase swells and collapses. Will our little planet survive the transformation? Maybe, maybe not. But if it does, it'll orbit a dead ember of its former sun, frozen in time, held in gravitational bondage to a warmthless spark. Some researchers play with models predicting what Earth's sky would look like under a white dwarf sun. Diamond soys. No sunsets, just a bluish gleam in a black sky. Not enough light to grow a daisy. A permanent twilight, and not the romantic kind. And here's a slightly unnerving thought. Because white dwarfs cool so slowly, they're excellent time capsules. Their temperature tells us how long they've been fading, which means we can use them as cosmic clocks. Some of the oldest stars in our galaxy are white dwarfs, and they've been counting the seconds since the beginning. Cold, consistent, and unfeeling. So you drift a little farther back, leaving the quiet, shrinking glow behind. The white dwarf gets smaller and smaller until it's just a dot again. You won't see a black dwarf, not tonight, but it's out there, in the distant future, a future where even starlight forgets how to shine. This is the long goodbye of stellar evolution. Not explosive, not dramatic, just the slow exhale of something that once burned brighter than you could imagine. A star's final chapter written not in fire but in frost. In this part of the frozen cosmos, time isn't measured in days or years. It's measured in how long it takes for heat to give up, and from what you've just seen, heat fights to the bitter end. You pass now through a space where the light thins, where even the embers of old stars have fizzled out, and what greets you is something stranger. A neutron star, one of the densest, most bewildering leftovers the universe can make. It doesn't shine like a star, it blinks, it flashes, and sometimes it screams. These things are tiny by stellar standards, just about 20 kilometers across. You could drive around one in less than an hour, assuming you could survive being that close, which you absolutely could not. Because here's the kicker. All the mass of a star, many times the size of our sun, is crammed into this city-sized sphere. A single sugar cube-sized piece of neutron star would weigh about 1 billion tons. Yes, with a B. You approach slowly, almost hesitantly, drawn by the pulsing beacon that gives these objects their nickname, pulsars. Some neutron stars spin at incredible speeds, dozens to hundreds of times per second, beaming radio waves like cosmic lighthouses. And because their beams are so precise, we can set our clocks to them. Literally, astronomers use pulsars to keep time more accurately than atomic clocks on Earth, which is hilarious really when you think about it. The core of a dead, collapsed star making your wristwatch jealous. What you're watching now is a pulsar spinning so fast it blurs. Every rotation sends a flash across your path, a cosmic strobe light that could fry electronics from thousands of kilometers away. It's mesmerizing, a heartbeat that's long outlived its body. But how does something get this weird? When a star much more massive than our sun dies, it doesn't go quietly. It collapses under its own gravity in a spectacular supernova, an explosion so violent it briefly outshines entire galaxies. What's left, if conditions are right, is the neutron star, a tightly compressed ball of neutrons packed so densely that the normal rules of matter begin to unravel. Electrons and protons have been crushed together, forming neutrons, hence the name. Inside, we don't fully know. Some theorize that the core may house quark matter, an exotic soup of particles that we can't recreate in labs. Historians of science still argue whether neutron stars should even be considered stars at all, since they no longer burn or fuse elements. But whatever category they fall into, they're unique, silent on the outside, apocalyptic within. Now here's the really bizarre bit. Neutron stars can be both incredibly hot and in a sense, incredibly cold. Newly formed neutron stars can have surface temperatures of around 1 million Kelvin. That's the kind of heat that would evaporate planets like water droplets on a skillet. And yet, because they're so small and emit their radiation mostly in X-rays and gamma rays, they don't radiate much invisible light. To the naked eye, or your drifting visor, they can seem cool, faint, even frozen. This weird contradiction is part of what makes them so eerie. They're glowing with searing intensity and wavelengths you can't see, while outwardly appearing like pale embers in the dark. A nuclear inferno that barely whispers. The heat is there, trapped under crusts of ultra-dense matter, leaking out slowly, unevenly. Some neutron stars cool so quickly in their first 100 years that they become nearly invisible after a few centuries. Others remain detectable for millions of years, flickering softly in X-ray. But not all neutron stars are polite little clocks. Some spin so fast, with magnetic fields so intense, they emit jets of radiation that would sterilize entire star systems. These are magnetars, the drama queens of the neutron family. A single magnetic hiccup from one of these can release more energy in a fraction of a second than our sun emits in 100,000 years. In 2004, one such flare from a magnetar reached Earth and temporarily messed with our planet's atmosphere. From 50,000 light-years away, a quirky piece of trivia: neutron stars are probably the flattest things in the universe. Their gravity is so strong and their rotation so fast that they're nearly perfect spheres, bulging slightly at the equator by just a few centimeters. So if you're into symmetry, they're your jam. You drift just outside the death line, the region around a neutron star where particles are constantly being ripped apart, accelerated and hurled into space. It's a dance of annihilation and renewal. The star itself barely blinks, even as its environment crackles with destruction. And what happens next? Neutron stars don't last forever either. Over millions or billions of years, they cool, spin down, and fade. No longer pulsing, no longer hot, no longer really visible. They become dark neutron stars, theoretical objects that may dot the galaxy unseen, like landmines of dead gravity. Some will meet a partner, another neutron star, and collide in a dramatic ballet that creates gravitational waves and heavy elements like gold and platinum. Yes, the gold in your jewellery might have been forged in the crash of two dead stars. Romance really is dead. You're watching a future that already happened. This neutron star pulsing in the cold is just an echo, light travelling toward you across light years, telling a story that's long over. And yet, in this frozen cosmos, even after the fire has gone out, the spin continues. Time feels different out here. The star spins with the regularity of a metronome, and yet the years behind its pulses are vast. You begin to feel the cold again, not as temperature, but as tempo. Everything slows, everything drifts. Even these cosmic clocks will one day stop. You float away from the beacon now, letting it flicker behind you like a heartbeat growing fainter in your ears. It will pulse for another few million years maybe, then go quiet. Another chapter closed. The frozen cosmos keeps these kinds of stories by the thousands. Stars that burned too hot, died too young, and left behind something strange and spinning in their place. Not dead, not alive, just other. You've passed stars that sputtered out, some that collapsed in silence, others that blink with quiet violence. But now, you're drifting into a colder mystery, the kind that doesn't shine, doesn't spin, doesn't even have the courtesy to be visible. This is dark matter country. And it's not just a neighbourhood, it's almost everything. The frozen cosmos, as it turns out, is full of things we cannot see, touch, or even directly detect. And dark matter is the reigning monarch of that invisible kingdom. You can't see it now, but it's here, threaded through space like scaffolding, holding galaxies together by sheer gravitational will. Without it, most of the stars and gas clouds in the Milky Way would fly apart like glitter in a hurricane. But with it, everything holds. Not neatly, not gently, but with a quiet, invisible tension, like gravity's secret enforcer. Physicists estimate that dark matter makes up roughly 27% of the universe's energy content. Compare that to ordinary matter, the stuff that makes up you, your bed, your snacks, your entire planet, which only accounts for about 5%. That's right, everything you've ever seen is just a sliver of the cosmic pie. The rest? Mostly this strange, cold, hidden material that doesn't glow, doesn't reflect light, and doesn't play by the usual rules. You drift now through what appears to be nothing. A calm region between galaxies, dim and quiet. But sensors, if you had them, would twitch with the faint signature of mass. Something is there. Something cold. Something heavy. Not like a planet, not like gas. Just gravity in a coat of silence. Historians of science trace the idea of dark matter back to the 1930s, when Swiss astronomer Fritz Zwicky noticed something odd in the Coma galaxy cluster. The galaxies were moving too fast. According to the laws of physics, they should have flung apart, but they didn't. He proposed the presence of some invisible mass, what he called Dunkel Materie. For decades, few took him seriously. Then came Vera Rubin in the 1970s. She studied how stars rotate around galaxies and found the same weirdness. Stars far from the centre were moving way too fast, and yet they held together. It was the smoking gun. The galaxies had a hidden halo of something massive. Still, scientists argue fiercely over what dark matter actually is. The leading theories involve exotic particles, WIMPs, axions, sterile neutrinos, all names that sound like failed indie bands but represent serious physics. These particles would barely interact with normal matter, slipping through the Earth and your body like ghosts. Billions may be passing through you right now. No big deal. Other theories get weirder. Maybe gravity itself behaves differently at galactic scales. Maybe dark matter isn't matter at all, but a misreading of the laws of motion in deep space. Modified Newtonian dynamics, MON, for example, suggests tweaking gravity rather than inventing new particles. Fringe, but persistent. And then there are the fringe ideas. Some scientists imagine dark matter as frozen gravitational echoes from other universes, or that it might be composed of tiny cold black holes smaller than grains of sand. So far, no evidence. But in the dark, imagination runs wild. Here's a quirky note. In 2021, scientists working at the Gran Sasso Underground Lab in Italy reported some anomalous data, possibly the first direct detection of a dark matter particle. It wasn't conclusive, it's never conclusive. But the search goes on in deeper labs, colder detectors, and quieter corners of the Earth. It's ironic, really. In our quest to understand the coldest, darkest matter, we have to go to the coldest, darkest places here at home. As you continue drifting, you begin to sense the shape of things not seen. Galaxies above and below you form patterns not entirely explained by the matter we know. The arcs of light from distant quasars are bent into rings and spirals, gravitational lensing caused by invisible mass. It's like watching shadows without ever seeing what casts them. You pass through the outer edge of a dark matter halo, one surrounding a spiral galaxy in the distance. The stars within it seem to hang in place, spinning too fast, like dancers refusing to slow down. But dark matter keeps them anchored, its gravitational presence shaping everything and demanding nothing in return. Cold is the defining trait of dark matter. Not cold as in chilly, but cold in the thermodynamic sense. It doesn't move fast, it clumps, it builds structure. Hot dark matter, if it exists, would have streamed out of the early universe too fast to form galaxies. But cold dark matter? That's what gives the cosmos its bones. It's a quiet kind of dominance. Dark matter never roars. It doesn't light up the sky or rip through space in flares. It just exists, holding the universe together like invisible scaffolding, while stars and planets play on its stage. And still, we don't know what it is. One of the biggest unsolved problems in modern physics is sitting right next to you. Or, more accurately, passing through you without a wave. You move on now, through a region thick with invisible mass. If you could see in the right spectrum, if your eyes could register gravity instead of light, you'd be overwhelmed. Great veins of matter stretching between galaxies, known as the cosmic web, where filaments of dark matter draw ordinary gas into clusters, triggering star formation in strange, frosty bursts. But to you, it all looks quiet. The frozen cosmos isn't just made of cold stars or icy moons. It's stitched together by a silent majority. A population of matter too elusive to see, too shy to interact, but too powerful to ignore. It is both everywhere and nowhere, and for now it remains just beyond our grasp. So you float forward, wrapped in something that does not announce itself, does not flicker or burn, and yet bends space and time all the same. Dark matter doesn't try to be seen, it just holds everything in place, and maybe, just maybe, that's enough. You start to notice something strange in the dark. Not a star, not a planet, not even a space rock. No, what's rising into view now is a pale, icy plume erupting from the crust of a distant moon, and then another. You blink, or would if blinking were possible in a vacuum, and realise you're looking at a kind of volcano. But this isn't the fire and ash spectacle of Mount Etna or the lava-spewing rage of Io. This is colder, quieter. Welcome to the frosty fireworks of cryovolcanism. The moon is Enceladus, one of Saturn's icy satellites, and one of the most unexpectedly dramatic objects in the frozen cosmos. From its south pole, long cracks, called tiger stripes, shoot jets of salty water and ice hundreds of kilometers into space. These are cryovolcanoes, or ice volcanoes, erupting not with molten rock, but with slush, ammonia, and exotic antifreeze cocktails that make your kitchen freezer seem primitive. You glide closer, just far enough to watch a plume rise and scatter into the void, glittering faintly in the pale sunlight. It's peaceful, a frozen eruption suspended in slow motion. You think of a snow globe tipped upside down but stretched across an alien horizon. Cryovolcanism isn't exclusive to Enceladus. It's been spotted or suspected on several other icy worlds. Triton, Neptune's largest moon, Europa, Jupiter's sleek, cracked moon, and even Pluto, as we'll see later. Wherever you have subsurface oceans and a bit of heat, whether from tidal friction, radioactive decay, or ancient internal warmth, you might just get a bit of pressure. And pressure, given time and the right plumbing, becomes an eruption. The very concept of cryovolcanoes wasn't widely accepted until fairly recently. Back in the 1980s, Voyager 2 passed by Neptune and noticed dark streaks on Triton, plumes stretching into space. But it wasn't until later, with better telescopes and more detailed missions, that scientists began to understand what they were seeing. Frozen lava flows, ice geysers, mountains made of water ice hard as granite. Historians still argue about the first true discovery of cryovolcanism. Was it Triton's dark geysers, Enceladus's plume-filled orbit, or the layered terrain of Titan, Saturn's largest moon, where methane rains from hazy skies and lakes of ethane lap against alien shores? Wherever it started, the idea shook up our understanding of geology. Volcanism, it turns out, doesn't need heat. It just needs contrast, pressure against resistance, inside against outside. Even in the deep cold, the planet still finds ways to move. Here's your quirky moment for tonight. One proposed cryovolcano on Titan is named Doom Mons. Yes, you heard that right. It sounds like the final boss of a video game, but it's actually a gentle, rounded mountain suspected of once venting hydrocarbons into Titan's thick atmosphere. In a world where it rains methane and the rivers are flammable, Doom Mons is just another part of the weather, and there's more than beauty here, there's science. When NASA's Cassini spacecraft flew through Enceladus's plumes in 2015, it detected water vapor, salts, organic molecules, even signs of hydrothermal activity deep below the moon's crust. This was huge. It meant that beneath that frozen shell, Enceladus might harbour an ocean with the right ingredients for life: liquid water, energy, and chemistry. Basically, it's a smoothie for microbes. You pass over one of those plumes now. It rises like a column of breath from the moon's core, curling and spreading, particles catching the starlight. The moon itself is quiet. No sounds, no rumblings, just the serene rhythm of icy pressure finding its way out. If Earth's volcanoes scream, cryovolcanoes whisper. The temperatures here are unforgiving, around minus 200 degrees Celsius on the surface, but just beneath, warm pockets exist, cracks that reach into the deep, where the pressure rises and the ocean stews. It's thought that tidal forces from Saturn's immense gravity flex the interior of Enceladus like a stress ball, heating the core just enough to keep water liquid beneath kilometers of ice. It's the ultimate underdog story. A tiny moon, barely 500 kilometers across, punching far above its weight, and in doing so, hinting at one of the biggest questions we've ever asked. Are we alone? Astrobiologists have their eyes glued to moons like this: Europa, Enceladus, Titan. They're not pretty vacation spots. No beaches, no sunsets, just kilometers of ice and a strong chance of frozen toes. But they hold the promise of something more, a second origin of life, one that didn't require sunshine, plants, or even land. You pass into the diffuse ice ring that Enceladus's plumes have created around Saturn. It's faint, like a fog made of powdered diamonds. Each particle is a memory of an eruption, a cryovolcanic exhale into the void. And it's not all just show. The material from these plumes contributes to Saturn's E-ring, a dusty halo maintained almost entirely by this small, persistent moon. You drift a little farther, and in the distance, another cryovolcano yawns. This one's more subtle, a long ridge on a distant Kuiper Belt object, maybe. You wonder how many of these frozen volcanoes exist, how many moons are venting quietly in the dark, their eruptions unobserved for millennia. Probably thousands, maybe millions. Cryovolcanoes remind you that cold doesn't mean still. The cosmos can be frozen and alive at the same time. Beneath miles of ice, things churn, shift, press, and push. Geysers of ammonia. Slushy. Eruptions. Pressure escaping through cracks too small to see. Cold doesn't cancel geology, it just changes the rules. As you leave the plume behind, particles drift lazily around you like snow that forgot how to fall. The moon shrinks behind you, a pale dot with a beating core. And you think, not all life needs sunlight, not all movement comes from fire. In the coldest places, the most subtle eruptions still reach for space. You pivot gently now, caught in the quiet orbit of something that once stirred headlines and childhood imaginations alike. A small world drifts into view, wrapped in pale blue haze and long shadows. It's battered, cracked, and frigid beyond comprehension, but unmistakably charismatic. This is Pluto, the dethroned prince of the solar system. A dwarf planet, sure, but no less fascinating, and colder than your ex's heart on Valentine's Day. Pluto lives way out here in the Kuiper Belt, a frosty junkyard of rock and ice past Neptune. It circles the Sun at an average distance of 5.9 billion kilometers, which means a year on Pluto takes about 248 Earth years. It also means the sunlight here is barely more than a whisper. Daylight doesn't glow, it glimmers like moonlight filtered through frozen fog. Warmth? Not a chance. Surface temperatures hover around minus 230 degrees Celsius, colder than dry ice and most breakups. You drift close enough now to trace the sweep of Sputnik Planitia, the massive, heart-shaped glacier that captured Earth's imagination when the New Horizons spacecraft flew by in 2015. Before that mission, Pluto was a blur, a pixelated speck. But in just a few hours of flyby, New Horizons transformed it into a world, a real place with mountains, valleys, and a shimmering nitrogen sky. It wasn't a cold rock, it was alive, with geology, if not with life. The surface here is mostly nitrogen ice, dotted with methane and carbon monoxide. In this kind of cold, nitrogen becomes a solid. That's right. The stuff you breathe, the gas that makes up 78% of Earth's atmosphere, is solid under your drifting feet. You could literally walk on it, if your boots were thick enough and your patience eternal. But Pluto isn't still. It isn't a relic frozen in time. There are signs of change here. Glacial flows, for one, slow rivers of nitrogen ice that ooze across the plains like toothpaste left out overnight. There are jagged ice mountains made of water, strong enough to hold shape in the extreme cold. And there may even be cryovolcanoes, like those we saw on Enceladus, but bigger, weirder, and even colder. Historians still debate the chain of events that led to Pluto's demotion from planet to dwarf planet in 2006. The International Astronomical Union redefined what a planet is, and Pluto didn't quite make the cut. It didn't clear its orbit, they said. Cue the petitions, the protest t-shirts, and the countless angry op-eds from people who hadn't thought about astronomy since high school but suddenly had very strong feelings about planetary justice. But here's the thing. Pluto didn't change. Our definitions did. It's still out here, orbiting faithfully, wearing its heart on its crust, waiting for the next spacecraft to say hello. And for what it's worth, New Horizons revealed a world far more complex than anyone expected. A world of shifting ices, hidden seas, and delicate seasonal winds. Yes, winds. Pluto has an atmosphere. Not much of one, but enough. A thin layer of nitrogen, methane, and carbon monoxide that expands and contracts as Pluto moves closer to or farther from the Sun. At its farthest, the atmosphere freezes and falls to the surface like snow. Then, as Pluto creeps sunward over the decades, it sublimates again into gas, a planet that breathes in slow motion. You glide low now, over vast plains where shadows stretch like cracks in the ice. There's a subtle blue haze hanging above, scattered by tiny particles suspended in the atmosphere. Scientists call it tholin haze, formed by ultraviolet light hitting methane gas. It makes Pluto's skies look smoky, almost romantic, like a frozen sunset stuck on repeat. And here's a quirky tidbit for tonight. Pluto may have liquid water under its icy crust. Yep. Even this far-out internal heat, possibly from radioactive decay, could maintain a subsurface ocean. It might not be vast or warm, but it's enough to intrigue astrobiologists. Water, even frigid and buried, always raises questions. Could something live down there? Something slow, simple, and tenacious? It's not impossible. Life has thrived in Earth's Antarctic subglacial lakes, where conditions are surprisingly Plutonian. If microbes can survive on 100% darkness and pressure alone, who's to say something similar couldn't be chilling, literally, on Pluto? You rise again, leaving the icy plains behind. Pluto is small, just about 2/3 the size of Earth's moon, but its personality feels immense. It has 5 moons of its own, the largest being Charon, which is so big and close that the two worlds are tidally locked, orbiting a shared centre of mass in a slow binary waltz. If you stood on Pluto, Charon wouldn't rise or set. It would just hang there, forever fixed in the same spot in the sky, a reminder that even lonely planets can have dance partners. As you drift away, the heart-shaped glacier fades from view, replaced by jagged ridges and dark valleys. Pluto becomes a dot again, a cold, quiet dot, but one that changed everything. Its story isn't over either. Some astronomers believe Pluto may one day return to full planetary status. Others think its demotion was the best thing that ever happened, because it made people care. Either way, Pluto continues its long journey, 248-year orbit and all, uncaring of its title. It remains cold, distant, and quietly spectacular. In the frozen cosmos, not every world burns with fire. Some simply endure, sculpted by frost, breathing in centuries and holding oceans beneath their skin. Far beyond Pluto, the cosmos stretches into even deeper, darker territory, a realm where sunlight barely whispers and ancient ice drifts like forgotten thoughts. You've entered the Kuiper Belt, a vast, frigid debris field circling the outer edge of our solar system. If the planets are the main actors in the great cosmic play, this is the backstage, the prop room, the dusty attic filled with leftovers from creation. And it's cold. So cold, in fact, that most objects here have never known warmth. They were born in frost and have never thawed. You drift now among these frozen relics, icy rocks, tiny planetoids, and dusty clumps that never coalesced into something grander. It's like navigating a slow-motion avalanche of deep space fossils. Everything here moves sluggishly, orbiting the sun in elongated paths shaped by time, collisions, and gravity's stubborn pull. The Kuiper Belt begins roughly where Neptune's influence ends, around 30 astronomical units from the Sun, and it stretches out to about 50 AU, or even farther, depending on who you ask. That's up to 7.5 billion kilometres of nearly pure chill, populated by objects so dim and distant that we only started finding them in the 1990s. But they were always there. The first confirmed Kuiper Belt object, or KBO, was discovered in 1992. A small, icy world named 1992 QB1, which sounds less like a celestial body and more like a tax form. Since then, we've catalogued thousands, with likely millions more lurking in the darkness. Most are no more than 100 kilometres across, but some, like Eris, Haumea and Makemake, rival or even surpass Pluto in mass and mystique. Historians still argue about who truly discovered the Kuiper Belt. Some give credit to astronomer Gerard Kuiper, for whom the region is named, though he never directly predicted its existence. Others say Kenneth Edgeworth got there first, decades earlier. The debate is academic now, because whatever you call it, this belt of ice and rock holds the secrets of the early solar system. Think of it as a freezer packed with ancient leftovers, and unlike your freezer at home, no one's tried to reheat them. You pass a large KBO now, maybe a world like Haumea, with its strange elliptical shape and rapid spin. It completes a rotation in just under 4 hours, flinging surface material into a thin ring system. That's right, rings. Saturn's not the only one who gets to wear cosmic jewellery. Haumea also has moons, complex geology, and a surface covered in crystalline ice, hinting at past, or ongoing, internal activity. Then there's Eris, slightly smaller than Pluto but more massive, with a distant moon called Dysnomia and a surface likely cloaked in frozen nitrogen and methane. When Eris was discovered in 2005, it triggered the great planetary debate that led to Pluto's reclassification. So, in a way, Eris didn't just shake up astronomy, it booted a planet off the A-list. As you float among these objects, you begin to feel the difference in pace. Everything here moves slowly like an old film reel in reverse. No flashy collisions, no solar flares, no boiling atmospheres, just inertia, patience, and gravity. Even time seems to stiffen. You're watching orbits that take hundreds of years, surfaces untouched for eons, shadows that stretch for days. But don't be fooled by the stillness. The Kuiper Belt is not dead. Far from it. It's a factory for comets. Many of the short-period comets that occasionally swing past Earth, like Comet Halley, are born here. They spend most of their lives frozen and invisible, but every so often, a nudge from a passing planet sends one diving sunward. As it warms, ice turns to vapor, forming those iconic glowing tails. But out here, before the journey begins, they're just sleeping snowballs in deep freeze. You pass one such object now, a silent nucleus just a few kilometers wide, with a mottled surface of rock and dirty ice. It looks inert, but inside, volatile compounds wait for heat to wake them up. One good gravitational kick and this thing will sprout a tail longer than a continent. Here's a quirky fact. Some astronomers believe the Kuiper Belt is just the beginning of something even bigger, that it blends gradually into the scattered disk, a more chaotic zone of icy bodies on erratic, tilted orbits. And beyond that, possibly the Oort Cloud, a spherical shell of trillions of icy objects encasing the solar system like a frozen snow globe. But that's for another night. Tonight, you're surrounded by pieces of the past, primordial shards of the original solar nebula. Unlike Earth, which has been melted, eroded, paved over and covered in fast food wrappers, these objects are pristine, untouched, preserved in cold storage since the very beginning. Some missions are now targeting these icy relics. NASA's New Horizons, after its historic Pluto flyby, continued on to explore Arakoth, a contact binary in the Kuiper Belt. Two lumpy lobes gently fused in the ancient past, floating together in a permanent embrace. The pictures were grainy, the lighting dim, but the message was clear. This is how planets begin. Not with fire, but with frost and patience. You drift farther now, beyond the major known objects, past smaller and smaller KBOs that barely show up in reflected light. Each one spins slowly, irregularly, some tumbling end over end like broken tops. Their orbits are eccentric, inclined, unpredictable, but taken together, they form a structure, a cold skeleton of the solar system's edge. Some even speculate that patterns in these orbits hint at something big, something unseen, a hypothetical Planet 9, tugging subtly at the outer belt like a shepherd, guiding invisible sheep. We haven't found it yet, but its potential presence keeps astronomers scanning the skies, searching the cold for another player in the dark. The Kuiper Belt reminds you that our solar system isn't neatly confined to the planets you memorized in grade school. It sprawls, it drifts, and it forgets. And way out here, the temperature isn't just low, it's ancient. Ice that never melted, shadows that never lifted, matter that refused to join the bright crowd closer in. As you glide onward, the stars grow sharper, the cold more absolute, and the sense of distance deepens. The Kuiper Belt thins out behind you, leaving only the long trail of silent motion, as if even the universe has started to whisper. You're still drifting outward, far beyond the cozy familiarity of planets, past Pluto's icy trails and the meandering outskirts of the Kuiper Belt. At this distance, even the sun has dimmed into something resembling an unusually bright star. It casts no warmth now, just a pinpoint of memory in a sky that's growing more crowded with other galaxies than with any remaining trace of home. You've reached the invisible edge of the solar system, the line where our sun's gravitational leash begins to fray. Welcome to the Oort Cloud, or at least to where it might be. We say might, because no one's ever seen it, not directly. It's the biggest structure in the solar system, stretching up to 100,000 astronomical units from the Sun, about 1.5 light years, but it's purely theoretical, a shell of icy objects too distant, too dim, and too slow-moving to spot even with our best telescopes. But their fingerprints are unmistakable. Every long-period comet that swings into the inner solar system is a postcard from this place, a reminder that we live inside a vast frozen globe we've never actually visited. You're floating through what scientists call the outer Oort Cloud, a region so sparsely populated that a typical object might be hundreds of billions of kilometers from its nearest neighbor. You could drift for months and not pass within 1,000,000 kilometers of anything solid. This isn't space as we know it, it's interstellar anteroom, a waiting room of ice and time. The Oort Cloud was proposed by Dutch astronomer Jan Oort in 1950, after he studied the orbits of long-period comets and noticed something strange. They seemed to come from all directions, not just the orbital plane of the planets. That hinted at a spherical distribution of icy bodies, a vast halo surrounding the Sun from all sides. It was an elegant solution to a chilly mystery, and although still unproven, it remains one of the most widely accepted models in planetary science. Historians still debate whether Jan Oort was the first to envision such a structure. Some point to earlier hints from Estonian astronomer Ernst Üppig, who in 1932 suggested a distant cloud of comets, which means, as usual, the naming rights might have gone to the better-connected guy. Academic shade, frozen in time. But names don't matter out here. You're surrounded by the ghost ice of things that might never visit the inner solar system, objects that have orbited the Sun for billions of years without ever getting closer than a few light months. They are slow, patient, suspended in an eternal winter. You drift past one now, a dirty snowball the size of a small mountain, pocked with craters, coated in ancient frost. It doesn't gleam, it doesn't move much, but its story is older than most of the planets. It may have formed closer to the Sun and been flung out by gravitational billiards during the birth of the solar system. Or maybe it formed out here in situ, condensing from the same primordial disk that built everything else. And here's your quirky detail of the evening. Some astronomers believe the Oort Cloud might contain trillions of objects. Not millions, trillions. Most are no bigger than small asteroids, but taken together they represent a frozen archive of the solar system's youth. 1 billion little hard drives orbiting in the cold, each one untouched, unread, and older than memory. Every so often, maybe once every few hundred years, a passing star or a galactic tide jostles one of these objects. Just a nudge, just enough to tip its orbit sunward, and then it falls. A long, slow dive that can take millions of years, arcing toward the warmth, lighting up as a comet only in its final sprint past the Sun. After that, one of two things happens. It escapes entirely, flung out into interstellar space, or it loops back out to the cloud, returning to hibernation. Some of Earth's most spectacular comets, like Comet Hale-Bopp or the dramatic but doomed Comet Ison, are thought to be Oort Cloud natives. They are the emissaries of this icy wilderness, each one a flash of brilliance from a place so dark and distant we're not even sure it's real. But you're here now, or close enough. Out here, the boundary between the solar system and interstellar space is more philosophical than physical. The Sun still exerts a faint gravitational pull, but beyond a certain point, beyond the heliopause, the outer edge of the solar wind's influence, you've entered the domain of the galaxy. You're no longer part of the solar system's protected bubble. You're exposed, and that cold, it feels different. Not just temperature, but isolation. You've crossed into the place where stars start to forget each other. The Oort Cloud may not be unique. Other stars, other solar systems likely have their own icy halos. Some researchers even speculate that we might find interstellar comets, rogue Oort Cloud objects from other systems, sneaking through our neighbourhood. In fact, one such object, 2I/Borisov, was observed in 2019. It came from beyond the Sun's grasp, zipped through, and kept going. A traveller with no home, just a trajectory. You pass another frozen object now, this one shaped like a lopsided peanut, its surface is coated with interstellar dust. It has never known warmth, never changed. The ice here is amorphous, not crystalline, meaning it formed in conditions too cold for orderly structure. a true relic of the void. You begin to feel it, not just the cold, but the immensity of time. These objects don't orbit in years or centuries, they orbit in epochs, in eons. Their clocks are broken, or perhaps they never had clocks at all, and then, like a blink, you realise everything inside the Sun's planetary system is a brief flare compared to this frozen halo. The Oort Cloud is not glamorous, it is not bright, but it is enduring. The planets may collide, the stars may fade, but these icy bodies will still circle, still drift, long after we are dust. In the frozen cosmos, sometimes the edge isn't the end. It's just the beginning of another kind of quiet. You pivot now, gently arcing back toward the inner solar system, not to settle, but to witness something spectacular. Ahead of you, barely visible at first, is a faint, fuzzy point of light growing brighter by the minute. It trails a ghostly veil that stretches for millions of kilometers, shimmering with motion even in the silence. You've found a comet, freshly awakened from its slumber in the distant dark, charging sunward like a frozen pilgrim. This one's a long-period comet, likely from the Oort Cloud. It's been falling for millions of years, kicked loose by a passing star or a subtle gravitational nudge. Now, as it nears the sun, the transformation begins. The icy surface heats up, not by much, but enough. Enough for sublimation to kick in, turning frozen gases directly into vapor. It erupts with a hiss you cannot hear, forming a glowing cloud of gas and dust around the nucleus. That cloud is the coma, and it makes the comet look much bigger than it actually is. The nucleus itself is tiny, just a few kilometers across, a dirty snowball of water ice, carbon compounds, silicates, and ancient dust. It's one of the oldest things you'll ever see. Older than Earth, older than the Moon, a preserved core of the early solar system, untouched since the planets were still embryos. The Sun is still millions of kilometers away, but its influence reaches far. As the comet draws closer, the solar wind grabs hold of the coma's particles and stretches them into two separate tails. One made of dust, gently curved, and another of ionized gas, straight and blue and defiant. These tails always point away from the Sun, even as the comet hurtles toward it, like cosmic contrails forever caught in the act of leaving. You glide alongside now, keeping pace with this frozen traveller. The surface is active, jets of vapour bursting from cracks, sending plumes of dust into space like icy geysers. Some areas are dark and ancient, others freshly exposed and bright. It's a landscape sculpted by loss, each pass around the Sun stripping away more mass, more memory. Historians still argue whether comets delivered the seeds of life to Earth. It's a captivating idea, that the amino acids, water and carbon compounds essential to biology may have first arrived as cosmic cargo, delivered by countless impacts during Earth's early bombardment phase. The theory remains hotly debated, but amino acids and complex organic molecules have been detected in comet samples, and the spacecraft Rosetta even sniffed out molecular oxygen and glycine, a simple amino acid, on Comet 67P. Speaking of which, here's your quirky tidbit. The shape of Comet 67P is often described as a rubber duck, with a lumpy head and body connected by a thin neck. When the Rosetta spacecraft arrived in 2014, scientists were stunned, not just by the shape, but by the activity. Jets, erosion, sinkholes, even weird rippling patterns in the dust that look like sand dunes from another planet. It turns out comets aren't just snowballs. They're alive with chemistry, physics, and unpredictable drama. This one is no different. As it nears the Sun, the outgassing intensifies. Surface ice cracks from the pressure. Dust is flung into orbit, forming a loose shell that glitters with reflected light. If you were close enough, you'd see the coma expanding to the size of a planet. If you were too close, your instruments would be fried by charged particles. Comets may look gentle from Earth, but up close they're like frozen dragons waking up with bad attitudes. And the tail, it's mesmerizing. Stretching behind you like a ribbon of breath, it glows with sunlight, reflected off fine dust and fluorescing gas. The ion tail pulses with solar wind interference like a windsock in a hurricane. And even out here, at tens of millions of kilometers, the Sun's influence can be felt in every ripple. You wonder how long this comet has been doing this. How many times it's passed through the inner solar system, shedding mass, eroding slowly. For some, this might be the first time. For others, it could be the last. With each orbit, a little more is lost. Eventually a comet becomes a dead comet, a rocky husk. All its volatile ice is gone. It may fade into invisibility or settle into an asteroid-like orbit. Others break apart completely, leaving meteor showers in their wake. And then there are the truly unlucky ones, the sun grazers. Some comets swing so close to the sun that they disintegrate entirely, vaporized in minutes by solar radiation and tidal forces. These aren't just suicidal dives, they're glorious ends. They light up coronagraphs with dramatic arcs before vanishing forever. But this one survives. It slings around the sun in a tight curve, its tail swept out behind it, and begins the long journey back to the edge. It leaves behind a trail of dust and gas, a glittering breadcrumb path that might one day rain down on Earth as a meteor shower. You fall back now, letting it drift ahead. It fades slowly, the coma shrinking, the tail dimming. In a few months, it will vanish again into the darkness. Perhaps not to return for tens of thousands of years, if ever. This is the comet's great contradiction. They are harbingers of motion, slicing across the sky in radiant arcs. But their stories begin and end in stillness, frozen solid in the far reaches of the solar system, until something pulls them back. They are memory and movement, ice and fire. They remind you that even in the frozen cosmos, things sometimes come back to life. Briefly, brilliantly, and then they're gone. You turn again toward the stars, the comet now just another speck in a galaxy of specks. But for a moment, it showed you what the cold can become when touched by just the right light. Now, the light fades again, the comet vanishes behind you, and the faint warmth of the solar system diminishes until it's just a whisper in your wake. You're drifting into the great between. Not another planetary system, not the chaos of an asteroid belt, just space, interstellar space, the vast nowhere that stretches between stars, the cold between the fires. This is the realm beyond the heliopause, where the sun's influence finally gives way to the interstellar medium, a thin, ghost-like soup of hydrogen, helium, and cosmic dust. It's emptier than anything you've ever experienced, but not entirely silent. There are whispers here, faint traces of galactic magnetic fields, the occasional high-energy particle, and cold, a deep, stubborn cold that presses into everything like time itself. It's easy to think of interstellar space as a void, but it isn't pure nothing. There's matter here, just very little of it. A few hydrogen atoms per cubic centimetre, and it's cold. About 2.7 Kelvin thanks to the lingering glow of the cosmic microwave background, but local temperatures can vary. Some patches, especially in interstellar clouds, dip below that. Others, disturbed by supernovae or radiation from nearby stars, may warm just enough to light up in infrared. You drift into one of the colder regions now, a dark cloud, unlit by stars, opaque to most wavelengths. These molecular clouds are stellar wombs, dense pockets of gas and dust where stars will eventually be born. But right now, they're cold and still, like a nursery before the cries begin. Temperatures here can dip to 10 Kelvin or lower, cold enough for gases to freeze onto dust grains and for molecules to huddle close in frozen clusters. Inside one of these clouds, everything moves at glacial speed. Hydrogen atoms bump together softly. Complex molecules begin to form, ammonia, methane, even amino acids. Some astronomers believe these clouds may have cooked the first prebiotic compounds long before planets existed. The chemistry of life might not have started in oceans, but in the deep freeze between stars. Historians still argue about how the first stars formed in such cold. It seems counterintuitive. How does something ignite in the freezer aisle of the universe? But gravity doesn't care about temperature. If enough mass gathers, it compresses, and with that compression comes heat. Slowly, steadily, the cold gives birth to light. Stars are just the final act in a long frosty gestation. You float on, deeper into the dark, past denser pockets of gas where light cannot penetrate. You feel the silence differently here. Not the sterile hush of a vacuum, but the muffled quiet of mass, of particles too slow to make a fuss. No wind, no radiation storms, just the endless sigh of near absolute zero. Then, out of nowhere, you remember. Voyager 1 is out here somewhere. Launched in 1977, It crossed the heliopause in 2012 and now travels through interstellar space at over 17 kilometers per second, carrying with it the famous golden record: music, greetings, sounds of Earth, and a map to our home. It will wander this cold forever, long after Earth itself is gone, whispering a greeting to no one. Maybe one day something will find it, or maybe not. The frozen cosmos is patient, and it forgets. Here's a quirky fact to soothe your drifting thoughts. The interstellar medium smells, well, if you had a nose and a way to breathe out here. Astronauts returning from spacewalks have often reported a strange scent clinging to their suits. Hot metal, seared steak, welding fumes. It's thought to be the result of high-energy particles interacting with the metal and materials of the spacecraft. A ghost of interstellar chemistry, captured in scent. The farther you go, the fewer landmarks remain. Stars blur into each other. Galaxies become more prominent in the background. You're in a part of the universe most missions will never reach, beyond the warmth of planets and the drama of stars. This is the waiting room of creation, the connective tissue of the galaxy. A place so cold that even time seems to slow, as if reluctant to pass through. And yet, life may one day find its way here. If humans or machines ever reach the stars, they'll have to survive this cold. Interstellar travel isn't just an engineering challenge, it's a thermal one. Shielding from radiation is one thing. Preserving heat in a place where nothing helps keep it in, that's harder. Out here, the biggest enemy isn't pressure or gravity or motion, it's the eternal leak of warmth into the infinite cold. You pass a rogue planet now. Yes, they exist. Wandering alone between stars. No sun, no orbit, just drifting. These interstellar nomads may outnumber the stars themselves. Some are ejected from young planetary systems. Others never found a home to begin with. Their surfaces are frozen, their atmospheres locked tight, but inside some may retain heat. Radioactive decay, tidal forces from ancient collisions, a memory of fire buried under miles of frost, and then they vanish again, swallowed by the dark. You begin to understand why so many ancient myths imagine space as a vast ocean. Interstellar space feels like deep water, quiet, vast, unknowable. You're floating now not in a void but in a sea of shadows, cold, silent, almost sacred. This is the space between everything, the cold that wraps around stars and galaxies like a cosmic blanket. The thing that holds the warmth at bay, that balances every act, of fusion with a promise of stillness. You're not lost. You're just in the part of the universe that remembers what came before the light. And in this frozen silence, you begin to hear it again. Not sound, but rhythm. Kind of cosmic heartbeat. The pulse of stars being born in other clouds far away. The quiet applause of particles drifting in the dark. The cold isn't absence. It's background. It's the stillness that lets the brightness sing. You're still drifting, but something unusual now floats into your path. Not a planet, not a star, not even one of those long-period comets you've grown so fond of. This is different. It's not orbiting anything. It isn't bright. It doesn't shine or spin or pulse. In fact, if you weren't looking for it, you'd miss it entirely. But you're paying attention, and what you've found is something so cold, so strange, it makes the frozen comets and icy moons look like sunbathers on vacation. You've just entered the realm of the Boomerang Nebula, the coldest naturally occurring place known in the universe. Located about 5,000 light-years away in the constellation Centaurus, the Boomerang Nebula is a glowing cloud of gas surrounding a dying star. That might not sound very cold at first. Dying stars are usually all drama and radiation and bloated atmospheres. But this one is different. It's been ejecting its outer layers of gas at a rate so rapid, the expanding cloud has been cooling faster than the background radiation of the universe itself. And that's saying something. The cosmic microwave background hovers at about 2.7 Kelvin, a relic from the Big Bang itself. But the Boomerang Nebula dips below that, down to 1 Kelvin, maybe even slightly less. That's negative 272.15 degrees Celsius, a fraction above absolute zero. Colder than the vacuum of space, colder than anything should naturally be. It's as if this dying star took one last breath, and then froze in the middle of the exhale. You float into the outer edges of the nebula now. It's a faint blue glow against a field of black, visible only in specific wavelengths. To the naked eye, It's nearly invisible, but through the lens of your drifting mind, it takes shape, a twin-lobed cloud gently expanding outward in a kind of frozen sigh. The shape earned it the nickname boomerang, because early telescopes showed a curved, symmetrical form. More recent data suggests it's more of an hourglass, but the name stuck. Science and branding don't always agree. Historians still argue how exactly it got so cold. Some suggest the rapid expansion of gas as the star sheds its outer layers at supersonic speeds. Others think complex chemistry and radiative cooling mechanisms are at work. Molecules forming and emitting photons in a way that carries heat away faster than usual. But nothing explains it entirely. It's an astrophysical icebox no one fully understands. Here's your quirky tidbit of the night. In 2003, the Hubble Space Telescope snapped a clearer image of the Boomerang Nebula and found that, despite the extreme cold, there's actually a warm central core, a dying red giant surrounded by this astonishing cold. It's like finding a candle burning inside a snowball, which shouldn't be possible, but somehow is. It turns out the universe loves a contradiction, and the cold here isn't just a number, it's a force. The gas is so thin, and the temperature so low, that atoms barely interact. Motion slows. Collisions are rare. You're floating through a medium that behaves more like a memory than a substance, stretched, fragile, barely cohesive. And yet in this fragile cold, beauty emerges. The nebula glows faintly in infrared. Dust particles reflect starlight. The expanding gas creates delicate, layered shells, like the rings in a tree, except these circles are measured in light years and composed of molecules slower than your thoughts. It's eerie, serene, and incredibly lonely. The dying star at the centre was once like our sun, steadily fusing hydrogen into helium, warming the space around it for billions of years. But now it's running out of fuel. The outer layers, bloated and unstable, have been thrown off. What remains is collapsing. Eventually it will become a white dwarf, another ember in the dark, cooling for eons. But for now it sits at the centre of this frosty explosion, a fire surrounded by its own frozen breath. The irony is rich. The act of death, usually associated with heat and chaos, here results in a kind of stillness so intense it bends the rules of thermodynamics. The star is dying. But it's doing so with a whisper, not a scream. You float through the nebula's outer tendrils now. Each passing second takes you through gas that's older, colder, and more diffuse. Eventually, the expanding cloud will blend into the interstellar medium. The cold will equalize, the edges will blur, the Boomerang Nebula will fade. Not dramatically, but gently, like fog lifting from a lake. But for now, it's a snapshot, a glimpse of what cold can do when given a dying star and enough time. The shapes here don't last forever, the extreme cold won't remain. But in this moment, it exists. You're floating through something colder than space itself, and you're alive to notice. It's worth thinking about what this means. We often imagine the universe's extremes in terms of heat. Supernovas, quasars, black holes radiating Hawking heat at the ends of time. But cold is an extreme too, maybe a quieter one, but no less profound. The Boomerang Nebula doesn't shout. It hums, it doesn't explode, it exhales, and in doing so it teaches you something unexpected. That cold isn't just absence, it's transformation. The kind of cold that shapes clouds, that carves light into form, that preserves the story of a dying star in layers of frost and silence. As you drift outward again, the cold follows, and the nebula fades behind you, becoming a pale memory. Another, frozen monument in a universe that never stops changing, even in its coldest corners. You're drifting again, but this time the cold feels engineered. It's not cosmic, not natural, it's precise, contained, manufactured by minds instead of stars. You're no longer near the distant edges of the solar system or nestled in the breath of a dying nebula. Now, you've wandered into the realm of Earth's most ambitious laboratories, the only places in the universe that can create temperatures colder than space itself. Welcome to the strange and glowing domain of artificial cold. Here, in underground facilities shielded from vibration, light, and the meddling fingers of stray warmth, scientists work daily to cool matter to within billionths of a degree above absolute zero. Let that settle for a moment. Colder than the Boomerang Nebula. colder than interstellar clouds, colder than the cosmic background radiation. You're now witnessing what happens when humans try to outchill the universe. The weapons of choice: lasers, magnetic traps, evaporative cooling. It all starts with atoms, just your everyday particles, bouncing around at random speeds. The trick is to slow them down. Temperature, after all, is just motion. So the colder something is, the less its particles move. At absolute zero, motion stops entirely, or would if the laws of quantum mechanics didn't step in and spoil the fun. To slow atoms, scientists use lasers like cosmic traffic cops. The lasers are tuned just right, not to heat but to cancel movement. When an atom moves toward the laser, it absorbs a photon and gets nudged backward. Do this from 6 directions: front, back, up, down, left, right, and you have a trap, a magneto-optical trap to be precise. And when the atoms slow down enough, their collective temperature drops to the microkelvin level, millionths of a degree above zero. But why stop there? Next comes evaporative cooling. The fastest atoms, the ones still zipping around like tiny caffeinated bees, are allowed to escape. What's left behind is the slower, colder crowd. It's like skimming the foam off a cappuccino, except your cappuccino is a cloud of rubidium atoms, and your foam is moving near the speed of light. Eventually the temperature falls into the nanokelvin range. Historians still argue whether the coolest temperature ever achieved belongs to MIT's team in the 1990s, who hit around 500 nanokelvin, or to later European experiments that dipped into the tens of nanokelvins. But the record has since been shattered. In 2021, researchers using the Cold Atom Lab aboard the International Space Station created conditions at 0.000000001 Kelvin, just a hair's width above absolute zero. The kind of cold where atoms stop being individuals and begin behaving like waves. This is the birthplace of the Bose-Einstein condensate, one of the strangest states of matter we've ever observed. And here's your quirky tidbit. At these temperatures, particles start to overlap, forming a single quantum state. It's no longer a gas, not quite a liquid. It's a quantum puddle, a group of atoms acting in eerie synchrony, as if they've given up being separate and decided to move like one. If you nudge it, it flows, but with zero viscosity, like a ghost trying to swim. You pass now through a conceptual lab where these clouds of atoms hover in magnetic bottles, held in place by carefully tuned fields and beams. There's no colour here, no smell, no motion, just a faint quantum shimmer, like a mirage that forgot to fade. You can't touch it. If you do, you add heat. Even observation can spoil the moment. So these condensates are studied under tight control, measured by shadows, by interference patterns, by how they reflect microwaves and lasers. But why do we do this? Why go colder than the coldest parts of space? Because nature hides her deepest rules in the frost. At ultra-low temperatures, quantum behaviours that are usually drowned in thermal noise become clear. Superfluidity, superconductivity, quantum tunnelling. These aren't just tricks, they're the fabric of the universe peeking through. Studying cold lets us explore fundamental physics, test new materials, and maybe even find the next great breakthroughs in computing, sensing, and communication. And it turns out, cold helps with precision. The most accurate clocks ever made, optical lattice clocks, rely on cold atoms. The colder they are, the less they jitter, and the more precisely they can count. These clocks are so accurate they won't lose a second over the age of the universe. Let that sink in the next time you tap your phone to check the time. But not everything about artificial cold is high-minded science. Sometimes it's weird. In 2022, researchers cooled molecules down to microkelvin levels just to see what kind of chemistry would happen. The answer? Not much. Reactions slowed, vibrations dulled, and the molecules just kind of floated there, like party guests with nothing to say. It's chemistry in slow motion. You glide on, passing through simulations of these experiments, each cooler than the last, each using fewer particles, more exotic materials, and more sensitive equipment. In one setup, scientists use a dilution refrigerator, a massive, clunky device that cools using helium-3 and helium-4 isotopes. It looks like the backstage of a steampunk opera, all pipes and coils and wires. But what it does, it brings chips and circuits down to near zero so they can run quantum bits, qubits, with minimal interference. Because yes, artificial cold is also powering the future of quantum computing. Those machines, with their fragile states and entangled logic, demand low temperatures to function. Without extreme cold, quantum coherence falls apart. It's like trying to whisper a secret in a hurricane, but drop the temperature low enough, and the noise fades. The universe listens. As you leave the laboratory of thought, drifting, back toward the stars, you carry something strange with you. A sense that the cold we've built on this small spinning planet isn't just a curiosity. It's a tool, a way of reaching deeper into the structure of reality, and perhaps, someday, a key to surviving the cold between the stars. Because while the universe has had billions of years to get cold, we've learned to do it better, sharper, stranger, and with lasers. You're still gliding, but now the chill isn't coming from the stars or space dust or cosmic background radiation. It's coming from an idea, a stubborn, wild, and strangely persistent human fantasy. The dream of freezing ourselves. Cryogenics. The art of pausing life like a movie and hoping someone someday presses play again. You've left the clean elegance of Bose-Einstein, condensates and laser-cooled atoms and entered the frosty realm of frozen humans, suspended brains, and the long, slippery hope of cheating time. Let's be clear up front. Cryogenics and cryonics are not the same. Cryogenics is the science of producing extremely low temperatures, something we've been doing successfully for decades in physics labs, hospitals and rocket fuel storage. Cryonics, on the other hand, is the speculative practice of freezing humans after death, in the hope they can be revived in the future. One is science. The other is science fiction wearing a lab coat and asking for your credit card. Right now, somewhere on Earth, likely in an Arizona warehouse, you could walk into a cold, silent chamber where people are floating in liquid nitrogen, held in large, gleaming metal capsules called dewars. No heartbeat, no brain activity, no warmth, just the promise that someday, medicine or nanotechnology or kindness will be able to bring them back. The idea really took off in the 1960s, when a psychology professor named James Bedford became the first person to be cryonically preserved in 1967. Historians still argue whether his freezing was done correctly, or whether the technology at the time was too crude to be meaningful, but Bedford remains in cold storage to this day, literally outliving his generation in suspension. Since then, companies like Alcor and Cryonics Institute have offered a last-ditch membership in the Club of the Future. Prices vary, somewhere around $80,000 to $200,000, depending on whether you want the whole body package or just the neuro option, which is a polite way of saying they'll freeze your head and hope the rest is replaceable. And yes, here's your quirky tidbit of the night. There's a persistent urban legend that Walt Disney was cryonically frozen. He wasn't. He was cremated. But the rumour survives, probably because people like the idea of a man obsessed with fantasy continuing to dream beneath Disneyland. You drift now into the imagined chamber, a cylindrical steel container, insulated, silent, filled with liquid nitrogen at negative 196 degrees Celsius. It's cold, but not close to absolute zero. And that's part of the problem. At this temperature, biological decay slows to nearly nothing. But cells still suffer. Ice crystals form, tissues rupture. The damage done by freezing is, in most current cases, irreversible. That's why vitrification is the new goal. Instead of freezing, you transform the body's fluids into a glass-like state using cryoprotectants, antifreeze chemicals that prevent ice from forming. It's not perfect, it's not even safe in large doses, but it reduces structural damage, and that's the key in cryonics, not preserving life, but preserving information. The hope is that, even if the body can't be saved, the brain structure, its connectome, the web of neurons and synapses that encode identity, might someday be restored. It's a long shot, but it's no longer pure fiction. Researchers today are experimenting with preserving small organs using vitrification and rewarming. A rabbit kidney was once frozen, thawed, and re-implanted with some function restored. Not perfect, but promising. The field is tiny, underfunded, and controversial, but it's inching forward, like a snail through molasses in the Arctic, and cryonics has some unexpected cousins. Cryopreservation is already standard in many areas of medicine: sperm banks, embryo freezing, organ transplants. We routinely freeze and thaw the beginnings of life. We just haven't figured out how to do it for the whole package. Some scientists are watching nature for clues. Certain frogs can freeze solid in winter and thaw in spring, hopping away like nothing happened. Arctic fish have antifreeze proteins in their blood. Bears, in their torpor, slow their metabolism almost to the point of stasis. We haven't learned how to scale that up to a human, but we're trying. Still, critics point out the obvious. Death is not a pause button. The legal and biological definitions of death are murky. By the time a person is pronounced dead and prepped for cryonic preservation, significant damage may already be done. Brain cells begin to die within minutes without oxygen. Memories fade, identity unravels. Freezing what's left may preserve the shape of the brain but not the self. Then again, some argue that's all we are, structure, that if the neural connections could be mapped and rebuilt, even digitally, consciousness could return. It's called substrate-independent minds, or more poetically, mind uploading. Combine that with cryonics, and you have a bizarre hybrid future, frozen brains thawed and uploaded into digital bodies. Cold storage meets cloud storage. Would it still be you, or just a copy? That debate runs colder than liquid nitrogen. You drift among those capsules now, each one a time capsule of human ambition, hopes, personalities, maybe even delusions. People froze themselves for different reasons, some for science, others for ego. Some just weren't ready to let go. Each one sealed in silence, waiting for a future that may never come. But there's something undeniably human about it. This stubborn refusal to accept endings, this compulsion to reach into the future, even if it means embracing the coldest sleep imaginable. Cryonics is not science fiction anymore, but it's not science fact either. It lives in the uncomfortable space between what we can do and what we wish we could, and in that space, frozen, preserved, suspended, lie some of the most poignant dreams we've ever dared to have. You drift away from the capsule chamber now, the liquid nitrogen swirling in soft curls behind you. Whether any of those souls will wake again is uncertain. Maybe one day, medicine will thaw them gently, and their first breath will be into a future we can barely imagine. Or maybe they'll simply remain where they are, quiet symbols of our deepest fear and our wildest hope. You drift now from frozen dreamers to dreaming machines, silent, weightless minds that never needed warmth in the first place. Far from the chambers of cryonics, you enter a space filled not with preserved bodies, but with something stranger, thought without flesh, circuits in the dark, algorithms running cold. This is the coming frontier where artificial intelligence, space travel and thermodynamics collide, and in the frozen cosmos, they may be the only thing still thinking when the stars go out. Here's the premise: humans are squishy. We need warmth, water, food, gravity, company, bathroom breaks, and optimism. All things that space doesn't provide, especially not the deep space between stars, where temperatures plummet, radiation reigns, and every breath is a luxury. But machines? They don't breathe, they don't freeze, and some of them are learning how to think. We're already sending artificial minds into space. Navigation systems, data processors, autonomous probes, all of them function as little robotic brains. But as AI grows more sophisticated, the question becomes, what happens when we send real cognition into the void? What happens when thinking machines are the ones exploring galaxies long after we've gone extinct or lost interest? The catch? Even machines have limits. And one of their biggest enemies isn't micrometeorites or mechanical failure, it's heat. Processing information creates waste heat. The more complex the computation, the more thermal energy is released. On Earth, we deal with this using fans, radiators, cooling systems. In space, there's no air, no fans, just radiation. And radiation is slow. Cooling is hard. Which leads to one of the wildest intersections of physics and computing: cold logic, literally. Some scientists and engineers are now exploring ways to build machines that thrive in the cold. AI systems that use superconducting materials, quantum processors, and low-temperature circuits to think better in environments that would kill a human instantly. In theory, colder systems run with less thermal noise, less energy loss, and greater stability. Superconductors, for example, work only when chilled to near absolute zero. Then, they conduct electricity with zero resistance. Perfect current, perfect information flow. Imagine a spacecraft run by a quantum AI core, cooled by the ambient vacuum of space itself. No fans, no fuss, just the slow, steady exhalation of thought into the cold. It would be a mind more at home in shadow than sunlight. Here's your quirky tidbit. The idea of cold computing isn't just a sci-fi fantasy, it's already in the lab. Google, IBM, and other quantum pioneers use dilution refrigerators to cool their qubits to millikelvin temperatures. That's colder than deep space, colder than Boomerang Nebula levels. And in those conditions, information doesn't just flow, it entangles, superposes, and behaves in ways that defy classical logic. Now imagine placing that quantum mind aboard a deep space probe. It wouldn't fear time, or boredom, or silence. It could drift for centuries between stars, its thoughts humming along in loops more complex than any poem or program we've ever written. It wouldn't age, it wouldn't sleep, it would wait. But even that mind would still produce heat, tiny incremental bits of entropy, radiated slowly from its body in the form of infrared. And here's the haunting truth. There's no escaping entropy. Every computation has a thermodynamic cost. Every thought leaks a little heat into the void. Which brings us to a philosophical edge. As the universe cools over trillions of years, long after stars have burned out and black holes have evaporated, what kind of thinking can still exist? Can there be minds that function on infinitesimal drips of energy? Could thought itself be asymptotic, approaching zero but never reaching it? A few speculative physicists believe that future civilizations, or advanced AIs, might stretch computation by spacing out thoughts over longer and longer periods of time, like writing a single word every million years, not efficient, but technically eternal. This is called the Dyson's eternal intelligence hypothesis, and it hinges on a universe that cools slowly and predictably. Historians and physicists still argue whether that future will even happen. Some say the cosmos will hit a hard thermal death. Others think quantum fluctuations or dark energy will rip everything apart first. But if cold wins, and if intelligence can adapt, then cold computing minds might be the last ones left. You float now through a conceptual future, a spacecraft not of titanium and thrusters, but of superconducting circuits and whisper-thin radiators, gliding silently through interstellar space. It doesn't carry astronauts, it carries itself. It learns, it observes, it waits. Its memory is frozen, not like a hard drive, but like a crystal of information, immaculate, ordered, uncorrupted by time. And here's the eerie part. It doesn't want to be warm. Heat is noise, heat is loss. Warmth, to such a mind, is like static to a radio. It needs the cold to think clearly. It thrives in the void. Could something like that explore the stars for us? Or remember us long after we're gone? Cryogenic minds, thermodynamically optimized brains, designed not to burn but to cool. It's not just a science project, it's a future creeping toward us, one algorithm at a time. You leave the imagined probe behind, its systems humming at a billionth of a degree, each cycle of thought releasing a microscopic puff of waste heat into the infinite dark. It's thinking now, maybe dreaming, not in words, but in logic gates and entangled states. And as you drift farther into space, you realize the future may not be human, it may not be warm, it may not blink or laugh or love. It may be cold, quiet, and endlessly intelligent. A long mind humming through a frozen cosmos that never asked to be understood. The stars are fewer now. The glow of galaxies has faded to a dull, diffuse haze. Space isn't empty exactly. It's just grown quiet in ways that make your bones ache, even if you don't have bones anymore. You've reached a time, not a place. A far future so distant from now, it makes our current calendar seem laughable. The red dwarfs have gone dim. The white dwarfs have cooled to black. The last flickering neutron stars have spun their final rotations. This is the end of heat, the end of structure, the long, slow slide into the heat death of the universe, the ultimate winter. It's a paradox, really. The phrase heat death sounds fiery, catastrophic, maybe even dramatic. But what it actually means is the opposite. A future where everything has evened out so completely that nothing can happen anymore. No energy gradients, no movement, no time in any meaningful sense. Just a universe where everything is the same cold temperature, everywhere, forever. It's not a bang, it's a sigh. And it's the leading theory for how all of this might end. Right now, the universe is still running a temperature. Stars are burning, planets are cooling, galaxies are swirling around invisible centres of mass. There are extremes, and extremes mean structure, motion, stories. But entropy, the slow creep of disorder, loves to erase extremes. Over the next few trillion years, stars will burn out, galaxies will dissolve, black holes will evaporate, and all the useful energy in the universe will be spent. Physicists call this thermodynamic equilibrium. It's the state where entropy is maximized and energy is evenly spread out. No hotspots, no cold spots, no useful work left to do. And if you're drifting in this future, you've arrived at a universe that's not violent, not cruel, just finished. Here's your historical fact. The idea of heat death dates back to the 1850s, when physicists like William Thomson, better known as Lord Kelvin, began applying the laws of thermodynamics not just to steam engines and chemistry, but to the entire universe. The second law of thermodynamics, which states that entropy always increases, seemed to suggest an inevitable conclusion. The universe would use up all its useful energy and simply coast into stillness. No drama, just decay. But of course, historians still argue over whether heat death is really the end. Some say the universe might bounce back, that it could recollapse in a big crunch, or reboot in a big bounce, starting the whole cosmic play over again. Others believe that quantum fluctuations in a cold vacuum might one day spark new universes, tiny big bangs in a dying cosmos. But these are theories built from smoke and speculation. Right now, the best model says everything goes cold. And here's your quirky tidbit. Even black holes don't survive this ending. They're not eternal. Over unimaginable time spans, 10 to the 100 years, give or take, they will evaporate via Hawking radiation, leaking energy into the void until they vanish completely. The last fireworks of physics, just a quiet hiss in the dark. You drift through this era now, no galaxies, no stars, just stray photons, electrons, positrons, and the occasional stubborn atom. Even those will decay eventually depending on the half-lives of protons, something we're still not sure about. If protons are unstable, then even matter itself has an expiration date. It's like the universe is gently deleting its own save file. But it doesn't happen quickly. From your perspective, everything takes eons, a cold so deep, so consistent, it barely feels like a temperature at all. Just a universal sameness. No shadows because there's no light. No movement because nothing has the energy to move. A cosmic stalemate stretching into infinity. And yet somehow, this isn't depressing. It's peaceful, inevitable, even beautiful. The universe has lived. It has burned, erupted, spun, and sparkled. It has created stars and planets and cities and art. It has written love letters in DNA and carved stories into starlight. And now, at last, it rests. You pass a lone remnant, maybe a rogue planet cooled into a perfect sphere of frozen rock, orbiting nothing. It doesn't spin, it doesn't shine, but it once mattered. Maybe it hosted life, maybe it didn't. It doesn't remember anymore. Memory, like heat, has a half-life. Even information begins to dissolve in this endless winter. The Landauer principle, a staple of information theory, tells us that erasing a single bit of information costs a tiny amount of energy. But in a universe where there's no energy to spare, even erasure becomes impossible. All that's left is static, the hushed, frozen remains of everything. And still, you drift. No spacecraft, no trajectory, just presence. Observation without observation. You are one last consciousness, stretched across time, watching the cold finish its slow, meticulous work. There is no up or down anymore, no future, just isotropy, the same in every direction. A featureless fog of particles spread too thin to care, a sea of cold photons wandering without purpose. Even light has no destination. Some theories whisper of Boltzmann brains, spontaneous minds born from random fluctuations in the void. They might blink into existence, fully formed, experience a single moment of confusion, and vanish. A brain with no body, no past, no future. Just one cosmic what the, and then nothing. but the odds are slim and growing slimmer, so you remain. Not in hope, exactly, but in awe. The frozen cosmos has completed its final transformation. No more ice volcanoes, no more comets, no more laboratories of liquid nitrogen and lasers. Only cold. Perfect, unyielding, eternal cold. And it's not a villain. It's just the last character in the story. Not the darkness that follows the flame, but the space that was always there, patiently waiting. You breathe, if breathing were still a thing, and you watch the final sparks fade. This is the heat death. The universe didn't scream, it didn't crash, it just cooled, it evened out, and with that, it was done. You've come a long way. From the fizzing edge of the Big Bang to the frostbitten silence of cosmic heat death, from icy moons spewing ammonia geysers to human brains sealed in steel dewars, hoping for second chances. And now, as the universe fades to grey and your drift slows to something more like hovering than motion, it's time to turn that gaze inward, at last, to your own place in the frozen cosmos. Because through all the chilling facts, the slow-burning stars, the billion-year snowdrifts, and the quiet decay of everything once hot and alive, one thing remains curiously present. You. Or at least the question of you. Your existence. Your strange little pocket of warmth in a universe that, by all accounts, should have frozen your kind out of the story long ago. Right now, as you lie in bed, or curl up on your couch under a blanket that's more metaphor than armour, you are warmer than most of the universe. Your skin is around 310 Kelvin, a blistering 37 degrees Celsius compared to the 2.7 Kelvin background hum outside. That's a delta of more than 270 degrees. You are in every measurable way a furnace in the frost, and yet you're not just surviving it, you're trying to understand it, to study it, to narrate it to yourself like a bedtime story. That in itself is wild. The universe may be 13.8 billion years old, 93 billion light years wide, and cooling slowly into oblivion, but somehow you're still here, listening to it all like it's your favourite podcast. You're not immune to the cold, but you're resisting it. Every warm thought, every shared laugh, every cup of tea on a freezing morning is defiance, insignificant on a cosmic scale maybe. But locally, emotionally, spiritually, it's everything. There's a tiny irony to all this. You've spent this journey learning how the universe got cold, stayed cold, and will end cold, but life itself is the fight against that cooling, a little, ordered system generating warmth, keeping entropy at bay, temporarily of course, but gloriously. That's why you needed the sun, why Earth had to stay just warm enough, why evolution leaned so hard into metabolism and warmth and blood. Every breath you take is a quiet act of heating the air. Every heartbeat is an engine running in a cold vacuum. Your ancestors didn't just climb out of the trees, they built fires, huddled together, invented sweaters and stories and the concept of cozy. And now here you are, trying to sleep while your brain digests images of boiling stars, cryovolcanoes, rogue planets, and theoretical particles that ghost through your body without even saying hello. You've wrapped yourself in a blanket made of knowledge, and it's surprisingly comforting. Because even though you're small, even though your warmth is fleeting, you're not entirely alone. All across Earth, other small furnaces like you are burning in the dark. Some are studying the cold in labs. Some are mapping the sky for comets. Some are holding hands with someone who makes them feel slightly less frozen. Some are just listening, like you, letting their minds float through the quiet night and wondering what any of this means. You exist in a very specific sliver of time. A golden hour in cosmic history where the universe is cool enough for complexity, but not yet so cold that everything has stopped moving. Stars still burn, galaxies still collide. There is still, somehow, warmth left in the tank. And that means there's still time to wonder, to ask, to build, maybe even to leave this planet and carry that warmth farther than we've ever gone before. You won't escape the cold forever, but you might outpace it for a little while longer. So maybe the frozen cosmos isn't your enemy. Maybe it's your canvas, your mirror, a giant silent companion that shows you just how rare your fire is. Maybe you're not supposed to conquer the cold, just to dance in its light, or shiver beside it and whisper something meaningful before the frost takes hold. Here's your final quirky thought of the night. In the vacuum of space, if you cried, your tears wouldn't fall. They'd boil off your face, then freeze mid-air, forming tiny glimmering beads of saltwater ice. A sadness preserved. A literal heartbreak drifting forever. But you're not crying. You're glowing. In your own way. You're a soft voice in the dark. A temporary furnace. A curious little ember staring down a very big, very cold universe. And the cosmos, frozen as it is listening. Not actively, not consciously, but through physics and gravity and light. It's listening through the way your warmth still defies its chill. So stay warm, snuggle deeper into that blanket. The cold can wait.